Just a rough guess. You're going to be good with a handheld?
Yeah.
You will? Okay.
Yeah.
All right. Okay. Good weight, big top.
We can walk around. But we can walk around.
Oh, okay.
Don't stop.
All right, thanks. Hey guys, I need to run to the restroom real quick. Here's some. I'm pretty sure I got the QR codes right. But it's easier to scan the QR code than it is the functional editing. So I'm trying to do that to be helpful. Etherpad is we're going to be going from for notes. I really need somebody volunteer to be the scribe to take the notes for the meeting, especially since I'm going to be driving this off my machine. I won't be able to do it. It's also very important that everyone put their name on the Etherpad for attendance or contribution, basically to get credit for your time in OCP. And then if you're not on the mailing list already, there's the bottom one is the link to sign up. And that is our main method of communication. So I gotta run to the restroom. I'll be back in a couple minutes. Well then. Oh, it's so no problem. Is there anyone in it? Is there anybody in there? Anyone on already?
No.
No. I mean, has anyone joined the hangout?
Oh, I don't know.
I'm just curious.
2 viewers, but it could be both of these.
Right. probably. Okay.
Now it says one viewer, so we did have a viewer.
Oh, me showing up. They okay. Is it pointed at the screen or what?
One's pointed at the screen, and one's pointed at the front, and I can change which one is up. So we'll be doing that.
Okay, so who's going to be taking notes? Need someone.
I would if I could from up here.
Can't do it. Well, actually, I can take the notes while you're presenting, as long as. Okay, so if you don't mind, are you good on your deck?
No, I have no idea what I'm. So kind of, I'm not sure which one.
This is how we work, man.
Yeah.
You can just get up and
Jason,
talk.
the
though.
correct
You're good at
phrase.
that.
Quit your whining, do it. How you handle this guy?
Okay. Well, if you've got the Etherpad open, you see the agenda. The agenda, first one on there, I remember correctly. I think this is- Just one of them.
Oh, actually, he's controlling that on his computer. I don't have it. Yeah, but if I swap back, it'll swap to what's on that screen right now. So yeah. Right?
Uh, all right, so we want to get the first one is the project update. Past submissions, upcoming submissions. Vast majority of what we're going to be talking about today, really for this conference as a whole, are probably upcoming submissions. By the way, if you need the links back up, please let me know, or I'll switch over to them. Pardon me? Sure. No problem. So what we were just looking at was the Etherpad, so that's the second one. Did anyone use the QR codes? Are they good? They work good? Okay, they work. All right. I didn't actually test it, I just trusted that it worked. You good? Okay. Back when the QR codes first came out, I said, they're actually where they're going. Good. Take it down. Yeah. Okay. Well, anyway, while you're taking that down, I'll talk about the submissions. And really, I'll go back to the history. Some of it I talked about in the presentation earlier, but I'm not going to assume necessarily that everyone was there. So everyone is familiar with. Let me ask real quick: is there anyone here who's their first attendance of a summit? Wow, most actually. Okay. All right. Then yeah, it might be good for context to sort of explain how this whole thing works. So Facebook initially stood up a project. A number of different groups. One of the groups was. Hear me all right? I don't have a mic, but I think we're probably good. Okay. One of the groups was the data center design group, and the initial specification from Facebook was their data center specification, where they talked about a number of different things, mechanical specifications. It didn't get into the design necessarily, but it described functionality of the design. In some cases, specified voltages and all of that. And that was the first contribution to the data center group. And for quite some time, it just kind of sat just like that. The industry, digested, saw it, and it was met, at least from the perspective that I was giving it, which was at the time an analyst. It was a positive thing. It was what's going to come of this, but it was met with positive feedback, and like, hey, this is going to further the industry. And in most of the other groups, this has happened. But the reason that they did is because it was mostly looking at the at hardware. Bring us back.
Sure. There's a lot of glitter anyway, so it's kind of questionable.
Is it my bald head?
No, it's the fact that that camera hits both those screens, and there's nothing I can really do about that with the controls.
So the other groups, right? They were all hardware. They were all products that Facebook open sourced essentially and allowed other equipment vendors to become potentially another provider to Facebook, but also to the industry in general for anyone who wanted to sort of take the same approach that was specified in those contributions. Data center group was somewhat of an outlier in that it was a submission for, as I said, the specifications of their data center, but that's really all about as far as it went. When you get down to the rack level, you kind of take for granted that the data center exists. And when you're outside of the data center, if you are the power provider, you know that there's a building that needs power. So on both ends of that spectrum, you have, for the most part, one side of a one-sided innovation boundary, I'll call it. But when you look at the data center, at least the design of the data center, you have an innovation boundary on both sides that it's kind of give and take, like, well, we don't know what the environment is. It may be very humid, it may be very hot, maybe dry, maybe this. So there's no single approach to cooling, for instance. You may not know what the voltages are. You may not know what the supply frequency is of your utility voltage. So a lot of unknowns on the upstream side. On the downstream side, you have the similar challenges. You don't know necessarily, what the density is going to be. I mean, it was. You might argue that it was kind of specified in the initial specification, but that particular application was Facebook's implementation, which, as we talked about in the previous meeting, didn't really meet everyone's needs. Right? They're a big organization. They've got a homogeneous environment. It isn't comparing apples to apples when you look at most enterprises out there. So the industry looked at it with interest and excitement, but when it came to adding to the data center group, it was mostly crickets. Because how do you innovate on what is already considered
leading edge and bleeding edge.
Good time already.
I got 10 minutes. And so, along those lines, we actually did have one submission from EDCS Power. At the time it was under a different name, but they have a different name now. And this was sort of to bolt onto that and to try to specify within the data center specification. It was that of DC Power, and they added to that and contributed that. It is in, if you look at the wiki, it is in the specs under review. We went through a good number of, we developed quite a few comments and recommended revisions and all of that. And so it's more or less in kind of the final stages of editing. I expect that fairly soon it will be pushed through as final form. And anyway, let's see. How long? You ready? You want to come up real quick? You don't even need to necessarily give a presentation. You can just talk about it. That's fine. I don't care. Yeah. So anyway, if you could come up and introduce yourself. You need a mic. Click here.
Probably not for this group. I can talk loud. I'm good at that.
Just kind of give a. Where? I'll just.
Hi, I'm John Meineke from EDCS Power. We submitted the DC data center spec. That DC data center spec was kind of a realization of, Facebook's infrastructure and how they've configured their system works really well. You can do it this way.
Oh, no.
Oh,
I'm
okay.
working it for you.
It works really well for what they're doing, but how do you drive adoption into any other environment other than a Facebook data center specifically? How do you change that 277 type interface? Because ultimately 277 is nice for US. But as soon as you start going globally, it causes certain challenges. As soon as you start moving outside other elements, you start having a lot of problems with that type of voltage infrastructure. Because, and it just starts to pose some problems. So ultimately, when looking at it, it became clear that as soon as you start saying in the back of the rack, when you have a 12-volt bus in the back of the rack, and that's all the server guys care about is 12 volts, your open innovation all the way upstream, all the way essentially to the medium voltage side of this whole of the data center. So that's where bringing DC into this equation starts to make sense, because you reduce the amount of conversions, you reduce the amount of I'll call it conversion overhead within the overall data center stream, which allows you to be more efficient, use more efficient converters downstream than are used now. So essentially what you end up doing with a DC system fully backed up 100% batteries, you end up essentially washing out against the, in terms of efficiency for a straight-in AC system versus a DC system. So it causes some very interesting things to happen, because when you start putting DC into this equation, you start eliminating a lot of these AC artifacts. You start eliminating a lot of the generator interface problems. You start eliminating a lot of the issues that start to happen in there. And then ultimately, down at the bottom in the rack end of it, the most subtle and interesting difference is you eliminate all the phase balancing that they were going through with the Facebook design. So the phase A, phase B, phase C load balancing, all that goes away. So as soon as you start eliminating things out of the stack that you have to do, and you start eliminating variables and risk out of what people have to do to integrate the overall power or the compute side of it, you start making it simpler for them, and they're able to do more work with the computers. And that's where eliminating things like this phase load balancing is so important with DC. So that's where we submitted the DC spec. It was built solely off of the Facebook model of how they put together their AC distribution side with a 3 megawatt pod, and distribution system, batteries, etc. So it's it was that higher level. I guess we were asked to submit it as a black box. The DC UPS is not necessarily specified as one particular configuration. We were able to submit again, from that, what the generator side looks like all the way down through the DC UPS itself. So that was something that was very important, because then we followed that on with then a open rack DC submission as well. That I think went sideways They said it was kind of the same as they have right now. So it kind of went sideways, and that led to some more technical innovation on our side, where we actually ended up eliminating the power shelves entirely out of the entire rack. So it allows you to have top-to-bottom compute in the open compute environment. So it kind of changes, our innovations on that concept of DC and what we can do with DC really caused a lot of things to happen for us, with, as a corporation, and then with the electrical design of when you start putting DC in there, of all the things you can start to eliminate. So that's, I guess, the short story.
Yeah.
I guess.
Do you want to go through the, I guess, I don't want to say engineering details of it, but more or less kind of like a block diagram level overview of the, we start with electrical design and that thing. Not the why necessarily, but really kind of the how.
Okay. Yeah, it was built, again, the open compute AC data center spec was built up a 1247 interface, medium to medium voltage, and a essentially transformer-based system. 3 megawatt generators, a bypass switchboard system, and that fed into DC UPSs. We were specifically asked when we made the submission to leave that as generic as possible. So to allow for anybody's DC UPS to fit into that type of arrangement, because there were multiple vendors at the time. So that broke out into an 800 amp distribution system, because realistically it's the largest practical breaker you can have in DC and have it be space efficient in any type of arrangement. So then that broke then into either overhead busway or other connection mechanisms down to the actual, the actual rows and racks. Because when you start, the interesting thing is when you start putting DC into a open compute environment, in the typical configuration, they're running the 2 triplets, and then they have the 48-volt battery stack in the center. If you have your batteries up at where they're supposed to be in a data center room, you have a DC UPS. You don't need that. You don't need that rack in the center. You don't need that 48-volt rack. And all of a sudden, you get another rack of compute. And so, since you get another rack of compute in that space, you start increasing the density of how these systems operate. And you also remove the batteries off the data center floor. That was one of the other big things that was a change from this type of perspective, because putting 48-volt batteries all over the floor in an enterprise environment is usually a non-starter, because you end up running around changing batteries all day. And people don't want to do that in an enterprise environment. And with the national fire protection codes, you're limited in the amount of hydrogen you can have in any one room, and then the air exchange requirements for those applications. And ultimately, that's why you have battery rooms in data centers, because you have a certain amount of sulfuric acid in the room, and you have to have a certain amount of air exchange to support that amount of sulfuric acid. You have a certain amount of hydrogen. If it reaches the volatile limit, problem. So, it's walking through this. It's the National Electric Code, NFPA codes. It was a very, I'll say it was a very simple look at the overall, trying to decompose what Facebook did in their original Facebook spec, and how to decompose that back into an AC, from an AC system to a DC system. Because there's a lot of blanks that I had to fill in, I'll call it, in between those 2 points, because they didn't necessarily match up directly from an AC system to a DC system. So we're looking at medium voltage transformers, AC switchboards, the DC UPS itself, open rack electrical interface, because obviously now it changes to a DC interface, and then a DC bus duct is something they have to have in there as well. The main switchboards changed, get greatly simplified from what Facebook's currently doing. The direct current UPS, I mean, when you're looking at this, it's AC to DC, standard 5,000 foot elevation. It's a DC UPS. Operates like a UPS, yes. The battery room, how long the building lasts. What normally happens in a data center is you're going to actually take the batteries and you're going to put them in a separate space, separate contained space. That separate contained space is managed with hydrogen sensors, and it has specific amounts of air exchange that's required by codes in the United States. I can speak to the United States because that's what I can say. I know, but in the United States, national fire protection codes require you have a certain amount of air that gets exchanged out of that room to prevent hydrogen buildup in the event that there's an issue. Yeah.
It depends on a lot of things. Depends on what type of battery. Right, there are several different types of batteries. There's VRLAs, VLAs, and they range anywhere from 2 to 5 years to 10 to 15. But yeah, so some of them off-gas hydrogen, some of them are sealed and you don't have to worry about it. Like what they don't. VRLAs don't require hydrogen.
Yeah.
They do VRLAs too.
And it comes on the acid. Let's say if you have one of the acid jar, even if there's still VRLAs have ports.
I thought for sure there was one but anyway, the point is that it just and it depends on the environmentals. And I'm pretty sure like wet cells, ideal conditions, 77.
Yeah,
77 Fahrenheit.
Above room temperature.
Yeah.
Above room temperature.
So if you go one direction, you'll get a longer capacity when you discharge, but shorter lifespan. Go the other direction, you get a longer lifespan, shorter capacity.
Yeah. 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 As a corporation separate from this submission, we've seen a lot of traction around the fuel cells, the microturbines, the other, I'll call it naturally DC sources. Because ultimately those natural DC sources make a tremendous amount of sense because you're not paralleling with the grid and then driving it back down through the data center anyway. Yes. Yep. Yeah. Yep. And then as long as you're not trying to take those things, parallel them back to the grid and push them up onto the grid, they're much easier to permit, much easier to deal with, much easier to handle, and yes, you get tax credits for doing it too. And also the power company loves you because you're not causing them to accept power in a regenerative fashion with a distributed gen operator.
There's some I'll call them leaders that are cooking and have even implemented fuel cells, but there's a reason why you don't see them as pervasive. I mean, it's still kind of still very much in development.
Yeah. Well,
Bloom is local.
It's load acceptance, load rejection, big things with fuel cell. So it's when you put load onto a fuel cell, you're taking load off of a fuel cell. You'll generally either undershoot or overshoot the voltage. That's one of the big issues. Adoption of fuel cells and other technologies like that, because when you look at it, fuel cells are DC. Most of the renewable sources ultimately are DC. So why not put it into a DC system? Why convert it unnecessarily? Why have the inverters? Because when you look at the data centers of today, the single biggest failure item is the output filter capacitors on the AC inverter. I mean, you're servicing those once a year because you're not because capacitors are designed to provide DC. That's what they're designed to do. They're not designed to provide sinusoidal, currents. They're not designed to support sinusoidal voltages because they heat up. That's why you end up servicing them so often. That's why they fail so often. So you end up in a situation where, that's kind of why DC, because that's what it expects. So sorry, I digressed a lot. The AC interface, ultimately, in the U.S., you're not going to change much more than about 480, 277 on the high side, 2,500 amps. Standard breaker configurations. So it's a fairly standard interface. It was written into the spec. It was meant to keep it compatible with the systems that are out there. It's meant to keep it configurable to the other systems that are that are in the market today. So, can I scroll down on here? Or?
Yeah, just press right. Press right on that arrow.
Right.
All right, that's okay.
Sorry about that.
I thought you were seeing
I broke it. Okay. Yeah, that's perfect. Yeah, that was next. Like I say, it was meant to be kept simple. The energy storage system, I think we actually just kind of went through that a little bit. Being able to interface traditional wet cells, VRLAs, lithium-ion, other type of outputs, inputs, other things. The DC output interface was meant to be, again, kept it simple and kept it generic to a lot of different companies. So it allows for the plus minus 190 volt system. The DC output, again, it was keep it generic. 800 amp breaker, standard motor, standard UL 489 breaker output for the system. Whether it has overhead busway or not is basically it was written in there as an option. And then a DC electrical interface was kept the Anderson power pole connector and for the interface to the rack itself. Mechanical design all stayed basically the same. Its goal is low operating cost, and all the other indirect cooling and all the cooling aspects were built into the data center spec. I didn't want to touch because that was not really the purpose of this. This is meant to be kind of a bolt-on element to the existing spec, so it was meant to keep it simple and not try to do anything else. So, questions? Yes. Mm-hmm. It's what would it be if they used the DC gate? What would they do? I would do it differently, to be honest.
To clarify, I think what you're asking is where did this come from, more or less, right? No. So the reason this was submitted was really as kind of an extension to previously submitted spec by Facebook. So within their data center specification, they specify certain parameters, one of which is the use of DC power. The team here, that's their corner of the business. So they expanded on that and said, okay, were you to do that, here's some more on how you would. Well, it's based on Facebook's, right? Because Facebook, now what generation, I don't know exactly, but it was there, at the very least, they have one implementation of it, of that particular spec.
Of an AC version of this DC spec. Yeah.
This is not based on operating data set. There are things that will be what is proposed.
Certainly, yes.
That's what I'm trying to say. This is not based on ideas.
Correct. Yes.
That's good.
That's very good.
Yep.
Any other questions? Thanks.
Thank you.
All right. So you're presenting, Cole?
Yeah, I'm gonna.
Okay.
Steve's gonna. If you ask any technical questions, Steve's gonna have to probably answer. But
Okay.
Is that okay?
So we're doing this a little bit out of order, but the reason. Doing a little bit of out of order, but by virtue of availability and timing and all of that. So just bear with me on that. So Cole's going to present contributions. Understand that this piece of it we'll get into maturity model later, which I think is going to be a big portion of the framework for data center group going forward. One of which is operations management, a subsection of that. You might call it orchestration, and that's really what these guys are all about.
So I've got and most of you guys probably know who I am. For the past 4 years, I've run the foundation, and you guys are going to be the first to know that I'm slowly migrating to a startup, and I'm still attached to Open Compute. In fact, I'm trying to embody all of the principles that Open Compute provided to everybody, which to me, you hear Frank talk about the unplanned garden, and that's certainly what this is. But for me, as a software guy, I always thought of Open Compute as an enabler for software companies to look like hardware companies, and you're going to see how that affects what we're sort of designing and how we're thinking about things. But that being said, I'm really happy that the data center group is sort of focusing, or at least having a focus on orchestration, because for the longest time, and I've got 20 plus years in enterprise data center. I come at the industry from a slightly different viewpoint than a lot of your really awesome hyperscale guys. I worked in colos. I worked on IT stuff. But even for me, and you can go to LinkedIn and see where I've worked, and I worked for a very large OEM. I ran open source and infrastructure strategy for this OEM internally, and I really, really, really hated out-of-band management. I really disliked the one-to-one relationship that I have with my servers, and I feel like every time I'd go in the data center and I'd talk to a server, I was like having to take care of my cat or my dog. And so I've always kind of said, we need to start treating our servers like cattle and not pets. And then Grant just told me it's not even cattle, because when a cow dies, you have to like deal with that cow. It's more like insects, and I like that. I told him I was going to steal it, and I didn't think I was going to use it this fast, but I think the sentiment is absolutely correct. So, and Steve actually was in the lobby this morning speaking with Frank, and Frank was checking in, and Steve was talking about, all of the efficiencies that this industry has brought into the IT equipment. I mean, there's, and we all know in cloud, the reason why everybody is saying that data centers as an investment right now is a race to zero is because you have guys like Jeff Bezos and guys like Mark Zuckerberg and Satya Nadella all driving costs down to compete, which means they're reinvesting in their own infrastructure, they're reinvesting in their capabilities. It's a bad proposition right now if you're going to just be a small 1-2 megawatt facility. But why would you even go build that data center? It doesn't make sense. Even in those small environments, we've got sort of two clouds coming. We've got the general cloud that we all know and love, and then we've got a new cloud forming. And we're all familiar with the iWatch, and it's coming out. But it's estimated that by 2020, we're going to have 40 billion devices connected, and that kind of infrastructure I don't think personally looks like the infrastructure that we know and love today. When you're building a cloud for the edge, you're not putting a 100 megawatt data center in downtown New York or downtown San Francisco. That's just not going to happen. So we need sort of an urbanized, very low touch, and that's the key, a very low touch environment. And so what we think that the industry needs now, and where we think we can add some value, is through this sort of orchestration. And it's not even so much orchestration for us. We just want to expose an orchestration abstraction layer away from the physical critical environments and hardware up to the next generation hyperscale workload orchestration and automation engine. So think about your OpenStack solutions as like a workload orchestrator, or the VMwares as like a workload automator. Mesosphere, StackStorm. You have lots of cool innovation happening at the software layer, but the first time I heard the software-defined data center, I heard it from Steve Herrod, and he was the CTO of the VMware at the time. And I started thinking, Can you guys hear me okay?
Do it. Should I use this? Well, we were using that, but that actually brought up a good point. Broadcasting.
Oh, yeah,
And
okay.
we wouldn't pick it up. So
Got it.
that was my oversight. So.
Okay, sorry about that. So, for those that are listening on the broadcast, I'm sorry, I probably don't want to spend that last 5 or 6 minutes talking about that again. You'll see this announced tomorrow as a reciprocal license. So, what we're committing here, what we've contributed to the foundation, is, to my knowledge, the first OCP-HL-R contribution to the foundation, meaning it looks a lot like the Linux kernel and less like OpenStack. So you can take it, you can modify it, but where the license is going to say you've got to give that technology back if you modify it, which I think is a good thing when you're talking about how to communicate with billions of devices. Lost my train of thought a little bit, but we were talking about value and abstraction layers. And so what we've come up with is a contribution that is going to, and we've got a good foundation for what's being contributed today, but we've got a whole roadmap of what we want to contribute. And this includes firmware, it includes software, it includes an interface, a dashboard interface, so you can start building stuff on top of this. But man, I don't know how to say this. We want to be the next generation out-of-band management solution. Or really, it's not we want to be. We want Open Compute to drive the next generation out-of-band management solution, where it's no longer about the legacy protocols of IPMI and DCMI. It's about using JSON or using JavaScript to touch an endpoint that is HTTP driven, and you control your hardware based on rules and policies. So the data center operator of the future, to me, hopefully, looks more like a DevOps person. And what DevOps has done to the Linux administrator, the system administrator. I think if we can agree on the right level of abstraction for data center and data center orchestration, then we can turn that data center operator into sort of a DevOps type person as well. And it starts here. So I'm sure while I've been talking, a lot of you have looked at this, and Open Compute being what Open Compute is, we've actually changed the form factor of this already. It's not to say that this form factor can't exist. But what you see here is basically a sensor management bus that hooks up to either an IPMB board or an OCP debug header board that sits in the server, and then lets you talk to that server and the critical environments. So first off, any questions here at all about what this does? Okay, good. Just think of this as a communications board for talking with either Open Compute or standard rack infrastructure. In addition to that, we're actually going to be coming out with a number of sensors. So it's interesting. There's a VC here in town. I'm sure everybody here knows them. Named Andreessen Horowitz. They're kind of big. I think they're investors in Facebook. But one of their top, they have this thing called 16 things, and one of their top things that they're looking for in investment purposes is what they call enterprise sensification. And I believe wholeheartedly in creating sensors. And going back to Steve Herod and the software-defined data center, it always sort of confused me how you could have a software-defined data center if you didn't know what the data center was doing. The data center today, the superstructure, the critical environments, and all of that stuff is so disconnected from the IT infrastructure and from the workload that our mission as Weber is to expose those critical environments, and we want to work with everybody in this world. We want to work with Emerson, we want to work with Schneider, and with Siemens. I mean, anybody that's doing critical environment stuff, we want to talk to them because we want to allow software application companies and orchestration companies to look at that data, so we actually can build a software-defined data center. And to that end, you'll see that some of these are very relevant to Open Compute. Others probably might be a little more relevant to Vapor and some of the things you're going to see tomorrow.
But again, your typical. Does anybody know how much your typical PCI-based VMC costs? Somebody here knows. Well, let's just pretend it's a couple $100. The economics of a couple $100 times 100 megawatts is a really expensive proposition. Not only is it expensive, but it's also power consuming. I mean, let's just say for a second that it takes 2 watts to power that VMC per server. Well, at 100 plus megawatts, you're talking about real savings if you're moving to a model that's abstracted away, and you're talking to your data center more like insects or cattle and not pets. So to that end, the previous board that you saw, hard tooled is roughly, we're estimating within 4 or 5%, about $10 to manufacture. So that $10 piece of board plus these boards, which are even less to produce, much less to produce, gets you to the same capabilities. In fact, not just the same capabilities, not the same out-of-band management capabilities that you see today, where you can interface with your BIOS and you can do very interesting things about the hardware that lives in the rack. But it also gives you access over a very standard RS-232 interface that allow you to do a lot more, like query your critical environments and expose those up. So now in hybrid cloud, if you're talking about workload orchestration and automation, it used to mean that hybrid cloud was just, hey, I had some on-premise, or I had some public cloud, or I had, sort of my IT closet, and I existed in a colo facility, and that was hybrid. I have something on site and I have something remote. But hybrid, what it was designed to be, and what it's actually turning into, is now you've got interoperability and portability for the workload to exist both on-premise and remote, whether that's public cloud or hosted. So if you've got multiple co-location facilities that you exist in, and you're paying a variable rate of cost per kilowatt or cost per square foot in one of those data centers, and one of them is in Phoenix, Arizona, and it happens to be very hot there, and the other one's in Minnesota, it happens to be very cool there. Well, if we can expose that up, if we can expose the metrics of that up to the workload orchestrators, and they say, hey, am I constrained by any network quality assurance? Am I constrained by any data durability rules? No, then the workload can just move. As long as the data exists on both sides, the workload can just move up to Minnesota, and you can power down and save yourself a lot of money, all again based around a rules engine. And we're going to have all of the interfaces for that framework and the API. We're actually going to give this away as software, as what do you call API software? I mean, of course it is, but we'll hopefully give this away to the open compute community and allow that community to hack on and extend the interfaces for that type of functionality. So again, just to recap, the contribution tomorrow is the beginnings of what we call OpenDCRE, which stands for Data Center Runtime Environment. I'm not a fan of the word DCIM, infrastructure management. At least the 22 years that I have in IT has always been reactive. It's always been a reactive thing, and even your current decent strategies today are very reactive. Runtime environments, and I was a Java guy for forever. Runtime environments are self-aware, and they're much more real-time. So we wanted to create sort of a real-time analytics capability to holistically look at your data center as a whole, and again, not just the server, but the rack infrastructure, and ultimately provide the insights for here's how an entire data center is operating. This is the health, right? And this allows us to do one very critical thing. The other thing I'm not a big fan of is PUE. And people might throw rocks at me for saying this, but I can plug a hairdryer into rack and measure it north of the rectifier or south of the rectifier, and I can get to a PUE number, which I think is just absolutely ridiculous. I want to measure efficiency based on a workload, and this eBay actually has been very vocal about how they measure performance, and they do it based on a URL load. And so their metrics around efficiency are in context of something. Well, the rest of the world, to say that I'm running at a 1.08 PUE just tells me how I got power from the grid over to my rack, and that, you know, and if I'm a hyperscale guy, or if I'm somebody who cares about a page loaded or an ad served or a transaction created or processed, I care about how much of that I'm doing, for how much money I'm paying, and how much power I'm delivering to my data center. So we want to move away, or at least we want to factor in PUE into a greater metric, which it's not new, but I think for the first time we can actually expose the elements to get to what we call performance per watt per dollar, where performance is defined. Performance is whatever you define, and we want to expose that part, you know, that interface as a variable for the API. So if performance is a transaction, then it's, you know, these million transactions per second or whatever, and you can actually put that into a model. And I think that I don't know where Jason is, but I think that ultimately the maturity model, as that gets extended, we can start pulling in some of this sanity. So we're not just measuring electricity, and we're actually measuring. We don't run data centers just to put data centers and IT infrastructure in them. We run workloads, and that's why they exist. So we think that measuring the workload in context of how much power you're delivering to that workload, and how well that's running, we think that's an important metric. And so the way we do this, and we actually do this across both Open Compute compliant servers as well as your standard EIA stuff. So if you have an Open Compute, so this is the existing motherboard. So we actually, you know, tie into existing BMC through the IPv connector on the motherboard, and then this talks to that controller that you saw, that sensor bus, and then that thing talks to something that I'm going to show here in a second, and I'll kind of talk about the architecture of it. But the net is through this RS-232 interface, you can talk to your IT equipment, and you can do this for very, very low cost. So the other board that we have, and Steve, how much are these to manufacture? Yeah, so the Open Compute motherboard integration for the debug header is probably $5 or $6, as opposed to a couple $100 for the existing functionality you can have solutions today. And so we do this through the OCP debug header. Now, that being said, we need your help. We need your help coming up with the right approach to attach all of this, because obviously anybody that runs an out-of-band management network today knows that, you know, you have to create separate VLANs, you have to create separation between your public network and your management network. And there's companies that, you know, absolutely hate out-of-band management. There's other companies that, you know, make rules around what switches you can talk to for your out-of-band management network, etc. So we want to engage not just this community, but the hardware management community and the OpenRAC community on how best to actually cable this stuff from an architecture standpoint, to make sure that there's a good path forward. As we move to the swarm-based capabilities of infrastructure, it's got to be easy to manage. It's got to be easy to cable, and we need to be able to rip and replace these things in and out. And getting to that state is something that we didn't want to just take a guess at. We've actually got potentially something to announce around this. I don't think we're ready to do it today, but we've got one approach that might work, but we're willing to listen to any other approach. So if you know of companies that have technologies that help drive communications in a simple way, we're open to having a conversation with anybody. And I think this is a discussion for this community to have, not we as in a company, but we as in a community. I think we need to talk about how you hook this up. And to that end, who here has played with a Raspberry Pi? Yes, pretty much everybody. So Raspberry Pi has this architecture called HAT, which is hardware attached on top. And what you see on the left there is exactly that. It takes the exact same form factor. In fact, you see the ribbon on the top that on the other side of that board will plug directly into a Raspberry Pi. So now the new Raspberry Pi that just came out a couple weeks ago, it's just a couple weeks, right? Maybe 3 weeks. You now have a quad-core ARM v7 capability right on top of the rack that's literally able to talk to your rack, and through our firmware and through the Open Compute software, which will be open source, you'll be able to start doing really intelligent things with your infrastructure at a much higher level, thereby, replacing or at least if you don't want that high-touch, high-cost relationship to a BMC, you can go this route, and you can save yourself some energy, you can save yourself a lot of money, and you can do it out in the open with the tenants that Open Compute subscribes to. So over on the right-hand side, you just kind of see a 42U rack. No, it's not Open Compute, but I think it's a standard Vizio. Such as pace of innovation. But over there, you can kind of see architecturally how the controller at the top would talk to the communication sensors, and then those would obviously talk to these individual components here. Those would be the hooked up to the IPMB connector or the OCP debug header. So that's it. That's pretty much what we're coming out with tomorrow. Like I said, there's going to be firmware, there's going to be software, there's going to be APIs. Most of this hardware, a lot of this hardware gets contributed tomorrow under the reciprocal license. So it'll allow us to make sure that as we innovate on top of data center orchestration, that we're doing it on the same protocols, on the same hardware, and as that evolves, we all evolve with it. So, questions? Sure. So out-of-band management versus in-band management, that was the question, right? So out-of-band management is literally out-of-band because it happens outside of the processor and the IT infrastructure itself. You have an external card, and you're probably familiar with some of these cards. Just off the top of my head, you've got cards like the DRAC. You've got the Dell Remote Access Console, which I believe talks to a Broadcom BMC. You've got the HP ILA, Integrated Lights Out, which talks to BMC. And that's what makes it out of band. And so from that perspective, the out-of-band management network is literally the physical network, the layer 1, layer 2 network that talks to these BMCs and allows you to do things like remote power on, remote power off, remote power cycle, suspend, reboot. So regardless of whether the IT equipment is on or off, you actually get the benefits of a remote call to control your infrastructure. Yeah?
It looks like everything you presented is socketed to motherboard. Would you ever go directly like a wireless sensor?
So the question was, would you ever go to a wireless communication? And it depends on what you mean by wireless. There are certainly things that we're thinking about that don't include wires, but when you start doing things like Bluetooth, or you start doing things like Wi-Fi, you've got a lot of interference there, and you're actually going to have a lot of bleed over. And we're not sure that. Now, that's something to investigate for sure. In fact, we were talking about it this morning. Having a built-in wireless network, but when you're talking about 100 plus megawatts or even more, man, that's a lot of Wi-Fi. That's a lot of signal, and I'm not sure what that does to a data center. We'd have to look at what the radio output and the footprint of that would be. I think it's a great idea. In fact, I recently saw a patent around something like this. But that's not to say that it shouldn't be investigated. It certainly should. But if we're talking about a solution that doesn't include cables and not using wires, that isn't necessarily your Wi-Fi, we are definitely thinking about that. Yes. Totally agree. And so the comment was, you know, it almost seems like it would be desirous but not feasible to have sort of one interface, one protocol, one capability, and I agree with that statement. And yep.
Let's say do you feel that whoever is one of the algorithms or are really without public or without their own benefit?
Right.
It's very hard to have just one piece of public.
Right. Right. No, absolutely. So again, just to recap, the comment was around, you know, who's going to control this, and does it require a sort of single benevolent dictator? And you know, I guess I can proudly say that we don't have a horse in that race, and I mean that to say that it doesn't matter to me because this is open source. Whoever that data center operator happens to be, if they've got an agreement with Foxconn or somebody else has an agreement with Quanta or you know, Emerson or whoever, Schneider or Leap, you know, Emerson, Rittal, whoever's building data centers, doesn't matter to me. If they want to control that experience, okay, they can put their own firmware on it. If they want to differentiate on that and they want to offer a closed ecosystem, no problem. They can do that. They can write their own firmware. They've got open source hardware to talk to. We're not actually trying to say it's like our way or no way. We actually want them to just, you know, create value for themselves by allowing the physical critical environments and creating abstraction layers above that really high touch, high cost environment that they're in today, so they can start managing their infrastructure slightly more smart. That's all we're saying. So think of this exactly like Linux. So, you know, you take the Linux operating system, and some people put Linux on their servers, some people put Linux on their desktops, other people put Linux in their cars. There's embedded Linux. We want this to be the Linux of the data center. So you can take Linux and you can make it do whatever you want it to do, and then you can either give it away. You need to give the changes you make away, but it doesn't mean that somebody else has to adopt those things. They can modify it and they can do whatever they want for it as well. Yeah, I don't, and so this, again, it's talking about the comment was around complete ownership, and you know, I'm not trying to. I don't think this contribution is meant to enable one person to have control of anything. In fact, it's quite the opposite. You certainly have an option. You have an opportunity to put Windows on your desktop or Linux on your desktop, and then when you choose Linux, you can put Ubuntu on there, you can put Red Hat on there, you can put SUSE on there. There's a bunch of different experiences you get, but the one thing, at least on the Linux side, that you're going to get with all of that is this thing called the LSB. All of these modern Linux distros come with Linux standards base, and LSB guarantees that things like dbus are in place and libraries in the same location. So as software is written for, you know, the kernel and the userland space, that when it's going to fetch a library, when it's going to grab something, it knows where to grab it from. And actually, that's all I'm trying to do is create those same interfaces in hardware out in the open so anybody can adopt them, as opposed to a bunch of vendors getting together and saying, hey, this is the very limited scope of what we're going to provide this community. We're going to hide everything, and if you want to touch the interface, you have to go through us. That's the only thing I'm trying to do, is sort of rip open the actual communication layer with your data center, so you can use any technology you want. And you know, I know full well that when we give this away, we're creating competitors for ourselves. I mean, there are going to be software companies that spin up and compete against what we're doing, and they're going to offer a solution. But guess what? The entire community wins when we do that, because they're still going to be using this hardware. It's still free. You can still get anybody to manufacture it, and just because they offer a different experience doesn't mean that doesn't mean that I feel like we haven't done a good enough job with our solution. I think we're building our software to make sure that, you know, the people we're talking to are happy about the experience that they get. But I mean, I say this, and it's very cliche, but a rising tide raises all ships. And inside of the open ecosystem, if you're not doing business with that mindset, then you're doing open sourcing correctly. So by doing this, I know that we're going to have competitors. I know there's going to be software companies that come up and they're going to say, hey, we're going to have a solution on top of this, and we're going to sell directly against, you know, us. But that's okay. I don't have a problem with that at all. Yes. Yes. Yep. So, I mean, a lot of that we actually get. We get some of the critical environments here, because this actually happens outside of the IT equipment. You know, I mean, you can obviously look internally for temperature, but I want to know what my temperature is on the outside. I want to know, you know, that gives me some insight into how well that data center is performing. Higher inlet temperatures mean higher exhaust temperatures. And, you know, I think it's time for the data centers to expose to us what we're paying per kilowatt hour. We know it, right? But why not have a software capability to plug it in? So, and that's why I said there's a freestanding offer for, and we've got lots of great big critical environments companies that are involved with the foundation. I'm not going to name names, but there's lots of people that provide those facilities, and the critical environments, and we should be talking to them. Like, why wouldn't they want to expose that information up to a workload? They're just going to sell more stuff. I mean, we want to make it attractive, and there's a whole nother thing that we're going to talk about. You'll see it tomorrow. But we want to make it attractive for people that want to do edge-based embedded clouds. We want it to be attractive for those companies to start building data centers again, because today the economics of building a data center, a greenfield data center for 1 to 2 megawatts doesn't make sense. It just doesn't. I mean, I'll be the first to say that that's probably an accurate statement. If I was doing 1 to 2 megawatts of IT infrastructure, I'm not going to go spend the $5 to $10 million per megawatt to build that. I'm just going to go to a wholesaler and just exist in a colo. But the economics of that can change. We are in a position to disrupt that ecosystem, and again, you'll hear more about that tomorrow. But aside from actually grabbing environmentals, which we get here, we want to talk to Siemens, we want to talk to Emerson, we want to talk to, you know, the critical environments guys, and be able to expose that. But as a variable, the cool thing about this is they can expose absolutely nothing to us,
and we could still go ask them. It's contractual, right? You sign your contract with your colo provider, and you know what your cost per square foot is. You know what your cost per kilowatt is, whether that's variable or not. Now you can plug that into into a framework and into a model, and you still get the benefits. Like, we still provide you benefits because you are still in control of your infrastructure. You know what needs to be data durable. You know what needs to be QoS at the fact level, and we'll still be able to provide you with a lot of benefit because you know the hard numbers. So whether they're given to you dynamically through sensification, or they're given to you, through a contract and you plug them in, we can still get you those critical environment numbers, and you can still do smart things with it. This is exactly why we built this company. This is exactly why we exist, is to try and bridge that gap and then go one step further, which is not just let our DSIM suites talk to our critical environment suites, but let's expose that out and let's look across all of our available infrastructure, both on-premise and in public cloud. If I know what I'm paying per kilowatt hour and what I'm paying per square foot, plus I know what I'm paying per month for choose your public cloud provider, and I know what I'm paying on-premise, well, if I can expose all of that data to something like Red Hat's Atomic or StackStorm or OpenStack or Mesosphere, now these guys can just move their workloads around where it's going to be the most efficient. And I say optimum, right? And optimum does not necessarily mean most efficient. Sometimes optimum means most performing. So we can at least start classifying I think it's nuts. So there was a U.S. general named Patton, and he said, fixed fortifications are a monument to the stupidity of man. And these big one-stop shop hyperscale public cloud guys, yeah, there's absolutely a growth trend for people adopting that. But if a meteor hits that site, they're going to have a bad day, right? Or a tsunami comes and wipes it out. It's not going to be fun. And I worked for a very large organization, like a very, very big bank. I worked for a very big bank, and we had a payment processing facility in Tampa. And I don't know if anybody here lives in Florida, but if you remember, like 2005, 2006, it's like 7 hurricanes that season, and I spent countless hours having to do. And this is back when F5 was called 3DNS. I had to move stuff up to the north, and moving stuff around is not fun, right? Creating environments is not fun, or it wasn't fun, at least in 2005. So all we're trying to do is bring the economics back down to some sane state that allows you to make intelligent decisions about, okay, I've got data durability issues for this tier, and I need to make sure that I cover that. So that might be when you talk about data, who knows if it's compliance data, if it's replicated, maybe HIPAA, maybe FedRAMP, it might be PCI or SOX, whatever. There might be sort of a classification of that tier of data. And I can at least logically start now building my tier 1 through tier 4 data centers inside of that, inside of a layer on top of the physical. I think the physical level of tier 1 through tier 4 data centers is the wrong way to think about tier 1 through tier 4. We need to replace high availability and infrastructure resiliency with infrastructure recovery, and our apps should not be these big monolithic, all built in. We should have some microservices that are redundant and capable, and we should be implementing design to fail philosophies as opposed to trying to create dual power supplies and making sure that the infrastructure is always alive. We should expect our infrastructure to die. That happens. It's hardware. It has electricity running through it. Eventually, it's going to die. So we should embrace the fact that hardware should fail, and we should be able to just pick up where it left off. The application should be smart enough. The data center should be smart enough, and the network should be smart enough to figure that out. So, and all of this technology exists. It's all there. So we're probably one of the, I'd say at least right now, one of the few companies trying to bridge the entirety of
you've got your fabric, you've got your physical, and you've got your IT equipment. How do we give you, the data center, enough information to make really good choices about your infrastructure and the workloads that run on them? I think that's good.
Yeah, would you clarify what you just said there about designing data center? Do you mean to fail over to another data center, something processing there, bank? I can't imagine that you want to have just any kind of an online banking investment operation going on inside of that center.
Yeah, no, I mean, I'm not saying like the physical superstructure should fail. Definitely not. I'm saying the application layer should be designed to fail, and the data layer should be designed to recover automatically and not have forcing functions for humans to go scurrying around like ants trying to fix something that's happened. Our infrastructure and our data center should be intelligent enough to say, okay, I've detected a big problem. Where can I go? Where can my workload go? Do I have the same data? Eric Brewer, back in the 90s, I think it was 95, he wrote the CAP theorem. I'm not sure if you know the CAP theorem or not, but the CAP theorem basically says you're never going to be 100% consistent and 100% available. So as an industry, we have settled on what we call eventual consistency because we care about data availability. We cherish availability we want a response, right? A response is better than no response. So if it's dead, it's dead. If it's wrong, well, eventually the answer can be right. So if you look at any block storage, any object store, any clustered file system, there's a metadata replication layer that happens there. So the first commit to the disk is always going to be different on that cylinder, on that head, than another disk on another cylinder, on another head, in another rack. The answers will be wrong. There's no physically, the laws of physics, you can only move at the speed of light. So, and just because you can move at the speed of light doesn't necessarily mean that your application algorithm is going to be smart enough to distribute that data across everywhere it needs to be replicated at the speed of light. There's no guarantee that the algorithms are going to do that. Yeah. I mean, the Tier 4 data center, and I believe in that. But if you're going to do a Tier 4 data center, then you can at least start using this to make sure that the data that is, and not all Tier 4 data centers house only Tier 4 apps. I mean, that's not the case. I know plenty of colos and wholesalers that have Tier 4 data centers with Tier 3 data in it. That happens a lot. So all I'm saying is, if it needs to be Tier 4, fine. And I came from the DoD. I know a little bit about Tier 4 data centers. I know Tier 4 plus. We were doing work on NIPRNet and SIPRNet, which are well beyond Tier 4. And there are physical redundancy in place, and I'm not saying that we shouldn't embrace physical redundancy. But cloud, in general, I would argue that a Tier 4 data center is not going to house your general purpose cloud infrastructure. You're going to throw that up the wall. Yeah.
That's a tier.
Yeah. Yeah.
So I love your idea of building the data center smart, right? It's sort of increasingly important to the advent of different cooling techniques, that kind of thing.
Yeah.
Have you considered corrosion sensors or a set to go alongside humidity pressure?
That's awesome.
It's a sensor for that.
Okay. So the bus is an RS-232. I mean,
The sensor level.
it's
Conditions.
oh right. So that would be an I2C, a condition I2C. So if there's a sensor for it, we could plug it in.
I don't know if there is. That's why I asked.
Okay. Yeah, I mean, it's funny because I do remember there's a big, heavily involved new company that, as they were first adopting humidified air, a lot of screws rusted.
Let's talk about it.
Okay. Awesome. No, that's a really good point. Thank you.
There is a sensor that can measure some gas and stuff.
I know concepts. I don't know wholesale. So if you know,
It's wholesale, but it's
There's a problem is,
MSA's got them off the shelf.
Very cool.
So what are you talking about? Translating Intel processor language into BMS?
BMS.
Steve might want to answer that question.
That's what we're tying into existing.
Yeah.
Ideally, like a processor level.
So Steve's telling me at breakfast this morning, he's like, I'm going to do some hacking. I'm going to plug something into a PCI interface and see how much I can get out of, over PCI. I haven't really given that much thought, but
in an ideal situation, we would propose the amount, what we would like to see come out of the motherboard, and have that another specification that vendors can build to. That is going to allow us to dig even deeper into the hardware than what we can now, without the addition of the expensive VMs.
right. And I think one of the places that we could do some work here with the community at whole is around the Redfish initiative. So you've seen Redfish, maybe you haven't, but I think it's HP, Emerson, Dell, Intel. They're working with, right now they're working with DMTF, and I know there's a specification coming, but if Intel's involved, I'm sure that there's going to be tightly integrated hooks into that, and we would love to work with Redfish if they expose something to the DMTF that becomes a standard. It wouldn't be the first time Open Compute has adopted a standard outside of that. We adopted IPMI, we adopted ECMI, so it's not impossible that could happen. The Digital Millennium Task Force, they're a vendor-based consortium. Vendor-led consortium.
The groups that I'm working with right now are a processor, a lot less active. Something that would be a system. Processor language is
Yeah. Matt, can we talk to you offline about that? Okay, that'd be awesome. Anything else?
Yeah, security. Viruses often brought into things like small, especially those that have some programming. Guys have thoughts about viruses.
Well, so there's plenty of open source Linux-based virus scanners, but we will be shipping a hardened interface, and when you see this, you're going to see one port open. There's going to be exactly one port open for the physical interface, and then there'll be one port open for interfacing with the touch point. So if we're going to have to do a good job to make sure that the interfaces, the rest APIs, no different than when OpenStack exposes open source APIs. The good news is it will be open, and if somebody wants to hack on the API, they'll be able to. But it's going to be HTTPS 443 for exposing the REST API, and it'll be 22 for communicating. On top of that, you're going to see a very hardened version of Linux running on it. There'll be, as far as I'm concerned, or as far as I know, there's no SNMP. We're not doing SNMP on it.
The only direct exposure networks controller rather.
Yeah, and that's another good point. The one kind of cool thing about this is it's actually going to be pretty hard for you to get into it. If you had a virus come into your public network, got a virus that was, it's obviously a big concern, for all of these Linux operating systems that are coming out now. You've got Floodlight, Big Switch, Open Network Linux, you've got Cumulus, you've got a bunch of Cura, you've got a bunch of software suites that sit and get installed right on top of your top-of-rack switch. This out-of-band management solution, you can call it that, sits in a completely different layer. I mean, it really doesn't even plug into your top-of-rack switch. So it would be hard to get, even if you compromise the out-of-band management solution, you're not getting physical access to the public network. Yeah, it was asked earlier, and right now the solution is all cabled. You need to cable it, you need to hard cable it, but we are investigating a number of different solutions around wireless. And by wireless, I don't necessarily mean Wi-Fi. I don't mean WPA and any crypto capabilities around Wi-Fi networks, but we do have some thoughts around eliminating wires. Yeah. I mean, I honestly think that if you were to try and write a virus for this, the only thing you're going to do is expose different information. You're not going to use this thing to get on the network. There's no attack that you're going to do to an IT piece of equipment running a mission critical workload. You're not going to have access to it. It doesn't talk to the top of rack switch. It's literally physically separated from the rest of your infrastructure.
Did you just say that you got remote reset on there?
We have a remote reset, but yeah, but you're gonna talk to that thing through a different. You're gonna talk through a different protocol and a different interface than going through your switch.
Like the Alpha, pretty fine. Out of band sensors were putting the I proved in my house in Wisconsin that I could take control of the lighting shovel up the bill, take control of it. Out of band, no problem, I can go and take control of it. So, A, you're plugging directly into EMS. If there's any mistake in that, you can run. But the fact that you have a remote reset on there causes anybody to get in there pretty easy chances.
When I said remote reset, I meant you'd have a function on here that will do a remote power reset, not this thing itself.
Sure. You had that 1,000 Facebook servers.
Didn't you know that there's a VMC on Facebook servers? There's already one there.
Okay.
And it's.
But making these sweeping comments, you know, I can't say that just for power side. I can't assume that I can find out the error. I'm going to have to have sensors probably tying into your system. I have to tie into your system. I can serve it because something happens. 100 kilowatts, 100 kilowatts of power.
Okay.
I'm just saying, the ability to do it, there's a chance of getting into your out of band.
Well, it's out of band, meaning should never be exposed directly to the outside.
Right.
That's
Sure.
the way BMCs are today.
Yes.
That's the way this.
And I've been involved in 2 systems that had that same idea that there's no way you can. So I'm saying there is no way. You shouldn't just stop designing out the security line.
Sounds like a network design issue.
It was dumb engineering. Well, there's a lot of dumb engineers out there, and I'm one of them.
So one of the things we're getting away from is small embedded internet-enabled devices cannot handle brute force attacks. They just die. They either reboot themselves, they die, or they open up in some manner that's a security risk. So one of the things we're eliminating by going this route is anything that has to come into our control has to go through a full-blown Linux hardened firewall, basically, of services that we provide and expose to the outside. These things in and themselves no longer are directly attached to the network. They are not network devices. They cannot be attacked on the network directly. Anything that has to touch these devices has to go through the controller at the top of the rack, which is running, as Cole said, a full-blown Linux operating system on a quad-core ARM processor, well capable of handling any of the threats that would be coming in, and would be able to stay current with the latest operating systems and patches.
And I guess just above and beyond that, I mean, I wrote the very first FedRAMP approved cloud offering. I know a little bit about security, but I don't claim to be a security expert. You know, I care a lot about security. We will make sure that, you know, despite that, we're going to have a very low touch, and in fact, we're going to have a lower touch interface to rack infrastructure than your present day out-of-band management solution, because it's literally sitting there attached to the same switch, and oftentimes, and it's right there, and if you can get into it, you can really wreak havoc. We don't use RJ45s. We don't have to use the RJ45 cable. If you look today at your typical BNC, your out-of-band management capability, it's an RJ45 with an IP address. We actually don't have to do that. We get that information over a different, it's not talking IP, which is one benefit. I mean, that is one, we do lower that risk level by the fact that it's not talking over RJ45 or IP. Yeah. Okay. I guess that's Jason's way of saying put the microphone down. So.
No. I'm just well, I was gonna say I was surprised.
But tomorrow we're going to announce a little more. And if you guys have any questions, or if you want to help us build this, I mean, this is going to be open source, open compute. And the last thing I'll say is, and I've said this on stage before, no single company has all the best engineers in the world. It just doesn't happen. Intel doesn't have it. Facebook doesn't have it. Google doesn't have it. There's a lot of smart engineers that exist across this industry. And communities like Open Compute are where these smart engineers can come and have intelligent conversations about what needs to happen. So we completely recognize that, and that's part of why we want to give this away as open source, because we know that we're not the smartest people in the room. And by working together, we can create robust, secure, scalable solutions. So thanks, Jason, and thanks all of you.
Let's take a quick break.
Yeah.
We'll take been in here for almost a couple hours now. Let's take, what do you guys want? 15 minutes? 10 minutes? 15? I saw a lot of heads nodding. 15. Okay, then let's make it, just before